All right, so today's lab is on Kirchhoff's rules. Um, Before I get into the lab, uh, I announced that there is quiz 2 available. You have until Friday midnight to complete it. As soon as you sit down, you'll have your 20 minutes to complete it within one sitting. So just make sure that you are um, prepared for it. It's going to be on the previous two labs. And as the semester sort of uh, becomes a bit more difficult as the labs continue, the quizzes might become a bit more difficult going forward. So uh, expect some math. Be ready for that. Um, if it is, I determine it to be more difficult, I will make the questions, or I will, have less questions. So yeah, keep that in mind going forward. Let me share my screen. Let me put this over there, and we'll get started. Okay, so we have lab 6. Let me put Kirchhoff's rules. I touched on this last week when we went over um, Ohm's law. Okay, this one is I could say almost identical to last week's lab. So if you found that one easy, yeah, it's really good. Uh, Today's lab will be sort of the exact same thing using the exact same simulation, but it's going to be a bit more complex. You can even see it's worth the most a lab has been worth this whole semester. So this is a real packed full lab. So going into the instructions, we will get to something that looks like this. Let me go up to the top. Okay, so remember, introduction, always somewhere near the top. I see people are writing like a sentence long introduction. Remember, it has to be a paragraph. I'm going to start taking off some larger points for very brief introductions. But here we have some theory in the intro instructions right here. This will actually help you if you don't like how I give my notes. These will be here for you to refer back to also. And I think they might be referred to later on uh, by equation number. Okay, so we're going to the same uh, simulations, the same one. You're going to click on that, and we're going to go to the same place, except, let me refresh, except in this one, we are going to the lab tab right here. Go to that, and it's basically the same. We have the same sort of stuff on the left. We have a bit more tools on the right, and we're going to carry from there. Okay, going instructions. Starting simple, 2 light bulbs and a switch. Measuring things. It introduces how to measure things again properly. Um, Something I can say about how to measure is try to keep the it instructs you right here, but try to keep the terminals. So when you're measuring voltage, let me show you. Say we're measuring a light bulb. Light bulb is right here. And a resistor. This isn't in the instructions. This is just my example. So say we're measuring voltage. we want to always keep the probes, these two leads right here, we want to keep them in the same order going throughout the circuit or whatever we're measuring. So to start out, I have electrons flowing. Let me put just the current sort of flowing direction like that. So I put the red side on the golden positive side of the battery, and I put the black side on the bottom, and I have a positive voltage. Now I try to keep this order of where these two probes are placed constant as I move it through the circuit. So if I wanted to measure through the light bulb, I would have to put this red one the farthest away from the battery and this one right here. And it's in the same sort of order. This red one is farther away. If I was going through this resistor, I'd move this red one down all the way to that point, and that black one would be on that point. Okay, so it just sort of, you think of the red one is leading the way. And that will keep, you see the voltages now have this negative sign. And we could actually consider keeping that negative sign later on when we're taking the values down. And they'll be a bit more clear when I go over my notes in a bit. Anyway, those instructions right there were recapped in this paragraph. So try to be consistent. Okay, so a simple arrangements, taking measurements. More complex arrangements, taking measurements. We're going to find out voltages and currents again. And it's going to turn into something a lot more complex, like this. We're taking measurements and finding currents. And this is maybe a bit complex for like calculating, but it isn't impossible to calculate. And this could be, a possible quiz question somewhere in a lecture, or I don't know if I'd put this on a lab, maybe, but it's not impossible, is what I'm saying. I think we're just measuring for today. Okay, and then marking values in this table as instructed. At the very end, we're going to be finding some unknown resistors using this. It's called a so there's a galvanometer, and I think the arrangement, possibly just the thing in the middle, is called a Wheatstone bridge. You learn more about that if you want to. Where was the link? There's a link right here. Okay, so another place that we're going to have to arrange it just like the picture and take measurements. You see, now we're finally done. Okay. 4.3. Okay, yeah. There's no place for a conclusion, so you have to add one down at the bottom on your own. Make sure the lab always has a conclusion and it always has an introduction. Even if there is no spot for it, you have to put it in yourself. Okay, so we have this lab. There's a lot of measurements to take. Since it is sort of the same, procedure, the same material, kind of as last week, I'm not going to have any things to check off. I'm just going to say whoever wants to stick around and work on it. I'm going to be here the whole time to help you out. If you feel confident enough to do all of these measurements on your own, that's also perfectly fine. But I do always suggest people stick around and work on it. Okay. So, are there any questions on this? On the procedure? Okay, let me go over some notes. And then we'll be on our way. Okay. Kirchhoff's rules. Ugh. Oh my goodness, I can't spell. All right. So we have the two Kirchhoff's rules. There aren't specifically numbered. They are known as the voltage rule, commonly also called the loop rule. Let me just put loop right here. And there is the current rule. Now, I told you to look these up last week, and I didn't want to go over them in too much detail because we have this whole lab on it right now. Let's see, current rule. It's also called the junction rule. Okay, let's do a little definition of each. The voltage rule, that is the rule that states that the voltage in any closed loop around a circuit, the voltage within any closed loop sums to 0. So how can we'll say the sum of voltage in any closed loop in a circuit, sum of voltage in any closed loop in a circuit is 0. So let me emphasize any, in any closed loop. I will highlight that in a bit. The junction or the current rule states that the current flowing into a junction is the same amount as the current flowing out of the junction. So let's say the current entering a junction is the same as the current exiting the junction. Okay, let me get some diagrams going. Let's start with something that we've seen last week. So we have a series circuit. We have a battery. And let's say it had 2 resistors. Like that. And the battery right here, let me maybe I could do that. Okay. This one is R1, this one is R2. And we saw this is just one big loop. Like that. How many things are in this loop? Well, there's one battery and 2 resistors. And last week we saw that we had a battery of 9 volts. And if these 2 resistors had the same resistances, they both shared the same amount of voltage. If you remember, they were both 4.5. This is where we could think about assigning a positive or negative sign to these circuit elements. I can, in my mind, it's easy for me to think of the battery is providing the voltage, so it will be positive. So that is a positive 9 volts. I keep moving the screen down. So I start out by saying positive 9 volts from the battery. Then I look at what else is in the loop. There's resistor 1, and it is consuming 4.5 volts. So with my notation, I'm going to say that's minus 4.5 volts. It's the same thing with that second resistor, R2. It is taking another 4.5 volts from the total volts, and we see at the very end we have 0 volts. This is good for this series example. Okay, and also we can be sure on these signs, or at least have confidence in these signs. I just made these negative, in that keeping those measurement probes, the positive and negative, the red and the black one, if I keep them in the same orientation, you saw how the battery was positive, and that's, confirms what I'm doing right here. And if I kept them constant and I go through the resistors, those gave negative voltages. And this is sort of proof of that, why you want to keep those consistent. If you're in a position where you can't, then you would have to just rely on assigning something positive and assigning something else negative. Whatever I assign the battery, it's providing voltage, I would have to assign everything else the opposite sign, that's consuming the voltage. Okay, now the other example, that's the more complex one. Let me shrink this because it is a bit big. So the other example, let me zoom in on these like this, is the parallel case. And from last week, I made this arrangement. Positive. I made this arrangement right here. Let's also look at the voltage rule for this parallel case. So the sum of voltages within any closed loop. Let me, again, any closed loop. Let's find the loops that are available. So there's this loop right here. No, let me make it a different color. There's this loop right here. That's called loop 1. That's just what I'm going to call it. And it's containing, loop 1 is containing R1. Let me just label this one out here too. That's R2 over here. So in loop 1, there is the battery, and there is one resistor. Following along, it's going through that, and around like that. Okay, let's write down what we saw sort of in our data last week. So in this case, we had the same voltage of battery, but what did we see for these resistors? We saw that they were both 9 volts. They were both consuming 9 volts each. So let me put this down here. I'm going to say the battery that's providing the power, I'm going to say that's positive 9 volts. No, let me do this in red so I know that this is the red. This is loop 1. 9 volts. And it has, in this one small loop, it only has one resistor. And that resistor is consuming the power, consuming the voltage. So that's minus 9 volts equals 0. And I could even without even measuring, say I didn't know this, I say 9 minus what equals 0. From the voltage rule, I know this should be 9 without even needing to measure. 9 volts. Okay, I think I helped a few people, and I showed them that there's also this outer loop happening with this parallel case. So if loop 1 is this small little area, what I suggested for loop 2 last week was going around the outside and making a big loop. So starting at the battery, going out and then around, and then going through resistor 2, and then coming all the way back around like this. And I'll call that loop 2. Now, what elements are in loop 2? There's one battery and one resistor. I'm making these big sort of, vague loops, but you just remember it's traveling along that path and then going through and then coming back like this. So the elements, there's a battery providing power, and then there's one resistor that's taking that power, and it sums to 0. There is a third loop in here, though, that I haven't talked about yet. That's the one right in here in this region. Let me just draw a picture of it. So this one. Call that loop 3. How can that be a loop, though, when there's no battery in it? Well, it's closed on all ends. It is considered a loop. Is the voltage rule also apply here? Yes, it does. Because the voltage rule applies for any closed loop. So saying if I knew the voltage that went across this resistor, I can use the voltage rule to find what voltage goes across that one. And since I called this one, so let me do this. Let me get the red back. Since I have this first loop that's going like this, that way through R1, and I have, and that yellow again, I have loop 3 that's going this way, and it's going that way through R1. Since these two sort of aren't, they're opposing each other, I'm just going to call R1, I'm going to call the voltage going through R1, I'm going to call that negative, since there's this opposition in the flow. So I'm just going to call that one negative. And that's commonly how we would just get through labeling these positive and negative without having a battery in here. And then I'm free to say that the voltage going through R2, what can it be? What does it have to be to sum to 0? It has to be positive 9. Does that mean it's providing power or it's providing voltage? No. It just means that it is completely countering that other resistor, the voltage provided by the other resistor, or the voltage flowing through the other resistor. Right, and so also, why am I calling R2 positive? You can look at just, I can also do this. So in this region, the red and the yellow, these two loops, the paths that I'm saying that they're going, I'm just choosing a direction for them since they are opposite one another, calling that negative. And then since the blue one is also going down like that, since those are the same direction, I'm calling that positive. Okay, so at this point, it really is just a matter of consistency and labeling positive and negative. I know that can be kind of the difficult part. For writing your values on the lab, I'm not going to be too critical on if something should be positive or negative. But on a test where you might have to remain consistent, you need to remember all of this. Let me put this. This is the voltage rule. Let me do the current rule real quick. All right, I'm not going to do a big circuit for this. It's mostly focusing on junctions. Just do that, that. Junctions, remember, are commonly just drawn as dots on a circuit somewhere. Okay. And, whatever sort of flowing charge, let's say that the current is going this way. And we're going to call that I1. That's the current, in that position. Let's call, let's say after the current from this enters the junction, it then has to separate. And it goes down like that, and then it goes over like that. I'm going to call this one down here I2. Call this one over here I3. So exactly like the definition above, the current flowing into the junction is the same amount as the current flowing out. So in this case, I1 would equal I2 plus I3. So if I1, if the current flowing into this junction was 9 amps, and say we only knew, say this is a test or something, and we only knew that the current over here on this side of the junction was, I'm going to put it down here, we'll just say 2 amps. Just do an example. That means we can say that the remaining current must have been split off into the second path. Because I1 is, that's 9 equals, and so it's just this simple problem. I2 is 7, so it's 7 amps. Flows this direction. Okay. Current flowing apart is the same as current flowing together through a junction. So I'm going to keep the labeling the same, but I'm going to change the directions. So let's say I don't know, like that, and like that, and like that. So what is the current flowing into the junction? That would be 1 and 3, because they are both going into the dot. And current 2 is the only one flowing out of the junction. So I'm going to write my equation like this. Current flowing out is the same as the current that had flowed in or entered the junction. 1 plus 3. This works with any sort of junction anywhere. Okay, think that's basically it for the notes. Are there any questions on the voltage or current rule, or you have something else you want me to go over? For the lab, remember I'm not going to be checking anything off today. I will make the groups. I'm gonna do that. Let me make the breakout rooms for people who want to work on it. Okay. Remember, there's a quiz out available. And yeah, let me do